Wouldn't it be cool if you could play back waveforms created in a simulator directly? Well, you can. I'm Professor Fiore, and I'm going to explain how. Welcome. We have a great video for you today. This involves being able to play back and also export wave files from Tina TI. Now, why is this useful? Well, we already looked at the import portion of this in a prior video, and certainly having a realistic waveform, maybe it's from a sensor, for example, maybe it's from a guitar, having that realistic input signal is very useful to us when we examine our circuit behavior, rather than having, a generic waveform like a sine wave or a triangle wave or a square wave. But more importantly, when it comes to audio circuits, your ears are what matter. So being able to hear the output waveform is extremely useful. And also being able to export that waveform in wave file, a very common format, so that it can be imported to other programs like a digital audio workstation or an analysis software package. That's really useful. So you can do all of this from within Tina. There is, however, one little gotcha, one little bug that I'll explain. So as I mentioned, you can import wave files of a variety of lengths, different types of wave files, 8-bit, 16-bit, different sample rates. You're not limited to a 16-bit, 44.1 kilohertz CD standard, right? You can use a 48 kilohertz. You can use 8-bit. Generally speaking, the greater the bit resolution, the better your results are going to be, but you do have this sort of option. Now, in order to use the playback and, more importantly, the export part of this, you have to use the loudspeaker device inside Tina. You can't just build your circuit in the normal way, put a voltage probe on there, and expect to be able to export. You can hear the waveform, but you won't be able to export it unless you use the loudspeaker device. More on that in just a sec. Okay, so you use this loudspeaker device in the same sort of way that you would use a voltage probe. You hook it in to the circuit wherever you need to export waveforms. Now, it's important to remember that this loudspeaker device, although you might think it's behaving like a loudspeaker in your simulator, it is not. This is not intended to be treated as a realistic loudspeaker load. In other words, something you would stick on the output of a power amplifier. That's not what it is. That's not what it's for. The default internal impedance on this is 1 tera ohm. Definitely not a regular loudspeaker. Now, regardless of the waveform that you put in, the bit resolution, you're going to get a 16-bit format out. It will, however, use the same sample rate as the input waveform. So if you put in a 22 kilohertz, 8-bit waveform coming in, you're going to get a 22 kilohertz sample rate coming out, but it is going to be 16-bit. But again, if you're using audio, you probably want to use a CD rate, 44.1 kilohertz, 16-bit depth, maybe a 48 kilohertz. Something along that line, all right? Now, the little gotcha that I had mentioned earlier is that inside Tina, there is something that looks like the loudspeaker device. That's not really the loudspeaker device. You have to know where to find this. Otherwise, this is not going to work, okay? So what I've done is I've built a little passive circuit here. This is just a double-tuned bandpass filter. And here we have a series resonance circuit. Here we have a parallel resonance circuit. So this is, at resonance, going to have a dip in impedance. This is going to have a max of at impedance. So what'll end up happening is whatever the input waveform is, we'll get basically that range of frequencies, right? Depending on what the Q of these things is, at the output. But at very low frequencies and very high frequencies, in other words, frequencies above and below the resonant frequencies, those are going to get attenuated. So what's going to end up happening is the output of this is going to sound kind of thin, tinny, honky, nasal. It's not going to have any bass, right? The high treble is going to be gone. You'll be able to hear it, but it's going to sound kind of cheesy, right? I mean, that's done purposely here to illustrate what's going on. So I want to show you how to get all these parts and so forth. So for the first thing, if you haven't watched the prior video on importing, I'll show you how to do that real quick. I've already set up an arbitrary input waveform over here, but it's very simple to do. You grab your sources, right? I'm just going to throw a source down here, double click it like you normally would, and then go into where you want to make your choice. And normally we would use a sine wave, maybe a square or a triangle. Instead, what you want to do is come over here on this last one. This is import wave file. So what you would do is click on load wave file, and a normal file chooser dialog box will pop up. Navigate around, find the file you want, click on it, and then the path will appear in here. These little buttons will light up so you can play it, pause it, stop it, rewind, and so forth. Now, because Tina doesn't know how big this voltage is sort of supposed to be, you have the option of setting this max voltage. It defaults to 1 volt. But, depending on what it's for, where it's from, you might need to change this. If you have maybe a recorded signal from a microphone or something, maybe it's only, 100 millivolts or so. So you want to alter that so that you can use this in your circuit, right? In any case, very simple setup, all right? So I've already done that with my arbitrary waveform generator. I've got about a 4.5 second snippet of a tune I wrote and recorded a little while back. So you can hear that. That'll be the input. Now, because that's a full range of instruments, at the output, here's our speaker output, we're going to hear that sort of pinched, thin kind of version because of this bandpass filter. Now, the question is, where does this little beastie come from? You would think it comes right here, meter, speaker. This is not the same thing. It looks the same. I don't know what happened here, but this is apparently a bug. I don't know if they have fixed this down the road, but I can show you this very simply just by clicking on the device, and you can see what's here. Okay. All right, it says 1 tera. This SP2, because I've chosen to be mono, that will be the case. I have tried this, and it just doesn't work right by itself. I haven't tried using this in conjunction with what I'm going to show you in a sec, but I do know by itself it does not seem to work. So there's some little glitch going on there. But in any case, this is how you're going to grab this thing. What you do is, it does exist, the proper version of this does exist in the examples directory. So you open up examples, go to the bottom, and you'll see something called wave file examples. Click on this, and there's a bunch of these things. So for example, you can grab distortion, and this is going to open up, there it is, a little distortion circuit, pretty simple circuit, and here's the thing you want. So you just grab this, copy it. Okay, I'm going to close this because I don't need it anymore. And then you can paste it in. Right, Control V, bonk. All right. So this is the device that you would place in here. That's how I got this. Now you might be asking a question. Why is this like :1 after the name and this is :2? This is one of those little kind of cool little things that Tina has that may not be immediately apparent to most people using this. I mean, I used Tina for a few years before I discovered, quote unquote, discovered this. This allows you, the number after the colon allows you to specify where in the output window, you want the waveform to occur. In other words, if you don't have the curves all collected together, if you have them separated, this will tell you the order in which they're going to be. Now, I don't need this anymore, so I'm going to get rid of it. So you'll notice I have varb:1, so this is going to be the first thing, and then spout:2, so this is going to be the second thing. I like that because I know at the very top there's going to be my input waveform, and at the output there's going to be, in position 2 right after it. And of course I can have other probes out here, to see other kinds of waveforms. But in this case, I'm primarily looking at just the input and the output because I want to see what this filter is going to do. And this sort of shows you what the process is going to be, right? You're going to build your circuit, you're going to simulate it, you have to run a transient analysis. Then you'll see the output waveforms, you select the waveform you want to hear, you'll play it back, listen to it, decide if it's what you want. If it's not, you go back, you tweak the circuit, rerun the transient analysis, play the output again. You can, like I said, go back and forth, compare them, listen to it. Is it what you want? Great. If not, go back, alter it again, and you just cycle through this process, right? Of changing the circuit, running the sim, listening to the output. How does it work? And you just keep doing this until you get what you want. I mean, it's a very fast process if you think about it compared to breadboarding something. Okay? And I will reiterate that you have to have this device if you want to export. If you just want to listen to it within Tina, you don't necessarily need this, but an export you do. Otherwise, it's going to look like, Tina's going to look like it's saving a waveform for you, but it doesn't. It, just disappears basically. Okay, so in any case, let's do a simulation. All right, so like I said, double tune bandpass filter. First, let's do a Bodhi plot so you can see what this looks like. I'm going to run from 10 to 100 kilohertz. All right, here we go. As a matter of fact, I'm going to collect these curves because it's going to look a little easier with the grid. So you can see what's happening here. These are slightly off tune and they're high Qs, so we get an interaction here. We get this double hump. But basically, here's 0 dB. You can see everything below a couple hundred hertz is being attenuated. Everything above maybe 1.5 kilohertz is being attenuated. Right in that area, a few hundred hertz, a little over a kilohertz, signals are actually being boosted a little bit. All right, so that's the frequency response. But can you tell what the sound is going to be like from this? I mean, you can get a gross idea, but not any kind of, sort of musical interpretation. So now let's turn our attention to a transient analysis. So as I said, I loaded up this little snippet of a tune. It's about 4 seconds long, so I'm going to run my display from 0 to 4.5 seconds, and we'll see what we get. All right, so again, varb:1, so that's at the top. spout is :2, so that's the second one. And then my vout over here from my voltage probe is just at the bottom, which of course is redundant with spout, right? In any case, I'm going to click on this waveform. Notice it lights up, and we see the little green arrow on the play, so I can play this now, listen to it. What does it sound like? And by the way, as it's playing, you're going to see a little like timing cursor go zipping across here to track it. Yes, a Eurovision hit. Now, so let's go over to the output, which you'll notice is at a smaller amplitude, right? 800 millivolts on the input, 500 on the output, plus all those frequencies are gone. So let's play this. All right, so like I said, kind of thin sounding, sort of tinny, maybe a little on the nasal side. You wouldn't really know exactly what it sounds like without listening to it. The visual is good. And, with a lot of practice, you can get an idea of what it's going to sound like, but there's nothing like actually listening to it. right? That's the real key. So like I said, if that was insufficient, I could go back and tweak my values here, run the transient analysis again, and repeat the process. Listen to my input, listen to my output, off we go. Now, to export, all right, so in this case, we can export SP out because the loudspeaker is there. So I'll go up to File, hit the export, select Wave. Now, a standard, file chooser is going to open up and, go to the directory, give it the name, and so on and so forth, and you're done. This will save as a 16-bit wave file. Whatever the sample rate was that you put on the arbitrary input, that's what you're going to get at the output. I think that's kind of cool. If you want multiple waveforms that you're going to export, you're going to need multiple of these little loudspeakers, right? So wherever you have a loudspeaker, you can export. You can listen in other ways. You don't have to have one of these for every place you want to listen, but for export, it does appear that you do need this, okay? Great. Okay, so extremely useful, I think, if you're doing any kind of audio work, because now you have this cycle where you can listen, tweak, listen, tweak, listen, tweak, right? And get things where you want a lot faster than doing it on a breadboard. Ultimately, of course, when you're done with all that, you do like to breadboard things, to get the final sort of ear okay, right? Plug a proper instrument, play. You can, fool around with dynamics and phrasing and stuff like that and see if the circuit's working the way you expect it to. But really, this is a nice frontline kind of thing, combining the arbitrary waveform input and then having this ability to listen to and export that sound, right? So you can kind of, make your own special effects. And when you export this, like you could take a guitar solo, let's say, make your own special virtual effects box, produce the output waveform, and then export that into your digital audio workstation. That's pretty cool. Right? Well, I hope you have found this to be interesting and useful. And until next time, this is Professor Fiore saying, take care.